Welcome back. In the second part of this section, we're going to look at the mean value theorem, which is our second big theorem of the day. This one has similar hypotheses to Rolle's theorem. We've got a function that's continuous on a closed interval. It's differentiable on this open interval from a to b, except here we don't have the condition that f of a and f of b have to be equal to each other. So no matter what happens, no matter what f of a is and what f of b is, we're guaranteed the following, that there's going to be a number, at least one of them, inside of our interval where f prime of c is equal to that little value that we've got there. And of course, we know what that is. If we're looking on the right-hand side of that equation, this is the average rate of change. Average rate of change over the interval from a to b. And of course, f prime of c, that's the instantaneous rate of change. So if we're thinking about some interpretations, what is actually mean value theorem telling us? I know the average rate of change, that's, of course, in addition to being the average rate of change, this is also the slope of my secant line that goes from x equals a to x equals b. So what I could think of it as, the slope of my secant line from a to b is the same thing as the slope of my tangent line at c. In other words, you've got the secant line through a and b, and it's got the same slope as of at least one tangent line on that interval. Or another way you could think about it is that since they've got the same slope, that the secant line and the tangent line would have to be parallel to each other. So you could also say whatever secant line we get from a to b, there's going to be a parallel tangent line somewhere that's tangent at c, that's somewhere in that interval. Or you could say the average rate of change over the whole interval is the same thing as the instantaneous rate of change at that point. And that one's sort of an interesting one. So pretend, if you will, we've got some sort of function that's telling us the temperature for the entire day. And let's say at the start of a 10-hour period, it was 20 degrees. And let's say at the end of a 10-hour period, it was 25 degrees. And so that the rate of change of our entire of the average rate of change over that interval, going from 20 to 25 degrees over a 10-hour period, is a rate of change of half a degree per hour. So on average, we're going up by half a degree per hour. Well, at some point between the beginning and the end point of that interval, the temperature must have been actually increasing at that rate of half a degree per hour. Or if you're thinking about a motion example, if you knew that, let's say, over a 1 hour period, you had covered a distance of 15 kilometers, in other words, your average speed was 15 kilometers per hour, well, then at some point during that interval of 1 hour, you must have been traveling at exactly 15 kilometers per hour. That's what the mean value theorem is telling us. So let's take a look at a couple of examples here. The first one, we've got a function, and it's f of x equals x squared minus 4, just on that interval from 0 to 2. So I have to confirm that the mean value theorem applies, and that means I have to confirm that the hypotheses are being met. And for sure, this is a polynomial function, and so it's continuous and differentiable everywhere. So I know that definitely it should be continuous from 0 to 2. So it's continuous on the interval from 0 to 2, and it's also differentiable on the open interval from 0 to 2. And the reason why, of course, is it's because it's a polynomial function. Polynomials are differentiable and continuous everywhere. So good for us, mean value theorem applies. So that tells us that whatever the secant line we get, there should be a parallel tangent line somewhere in that interval. So that's what we're going to do in 2 stages. First, we're going to find our equation of our secant line. And so for that, I just need to do a little bit of calculating. thinking. I know what the x values are for my secant line. I've got x equals 0 and x equals 2. And I need to find out what y is. And so for y value when x is 2, that's x is 0 rather, that's f of 0 or negative 4. So the first point on our secant line is 0, negative 4. And for the second point on our secant line, if x is 2, the y value is f of 2, and that turns out to be 0. So the point 2, 0 is on our secant line. And then for the slope, that's of course just the change in the y values over the change in the x values. So I'd have 0 minus negative 4 over 2 minus 0, which is a slope of 2. I also happen to notice here, just as a little aside, that one of my points happens to be my y-intercept. So when I create the equation of my secant line, I'm just going to use my slope-intercept form, y equals mx plus b. So for my secant line, my slope was 2, and my y-intercept was 4. So there we go, y equals 2x minus 4. There's my secant line. Okay, so follow-up. We said the mean value theorem applies, so somewhere between 0 and 2 there should be a parallel tangent line. So let's find the tangent line that's parallel. First off, we know parallel tangent lines, if I wanted to find the slope of a tangent line, that's the same as finding the derivative, so I guess let's get our derivative going first. Our function was x squared minus 4, and the derivative there is 2x. So if I've got a parallel tangent line, I would need my derivative to have the same value as the slope of my secant line, and my secant line had a slope of 2. So I would need my derivative to be equal to 2. And conveniently enough, the value for x that I found is inside my interval. Remember, I'm guaranteed there's going to be at least one value inside that interval. That doesn't mean that you won't find more than one value in that interval, or you might find values outside of that interval, but you're going to be guaranteed there's at least one that will be inside that interval, and that value x equals 1 definitely is inside our interval. So to get our tangent line going, we know it's going to be happening at x equals 1. We know what the slope is. The slope is 2. So we need our point to be figured out, and then we'll be ready to go. When x is 1, the y value is f of 1, which is 1 squared minus 4, or negative 3. So our point is 1, negative 3. And so now our tangent line, the equation for that is y minus the y-coordinate equals slope times x minus the x-coordinate. And I've got my second equation, the one for my parallel tangent line happens to be y equals 2x minus 5. One thing that I'm not going to do here, but I'm going to leave that as a little exercise for you to do for fun. This is a relatively easy function to graph. It's a parabola opening upwards with a y-intercept of negative 4, has x-intercepts at 2 and negative 2. If you were to graph that and then graph both of these lines, you would see that number 1, the lines are parallel. Number 2, the tangent line does touch at 1, negative 3, and the other one, the other line is indeed the secant line. So I'll leave that as a fun thing for you to do. Let's do one more example here. We've got a cubic function. This one's also a polynomial, so of course, same reason as before, we're going to have the mean value theorem will apply here, that g is going to be continuous on the interval from negative 3 to 3, and that g is also differentiable on the open interval from negative 3 to 3. And again, that's because it's a polynomial function. We know polynomials are continuous and differentiable everywhere, so it's definitely continuous and differentiable on that interval that we've been given. If we're looking for the average rate of change, we know if I'm looking for the average rate of change on the interval from -3 to 3, that I would look at f of 3 minus f of -3 over 3 minus -3, the change in the y values over the change in the x values. And this isn't a hard function to evaluate on the side here without doing in advance. So if I put in 3 for x, f of 3 would be 27 minus 12, which is 15. When I put in -3 for x, I'll have -27 plus 12, which is -15. And 3 minus -3 is 6. And cleaning things up, I'll have 30 divided by 6, which is 5. So my average rate of change for g on that interval is 5. And I just realized it said g, so I really should say g of rather than f of. Let me just fix that. There we go. All right, so our average rate of change is 5 over that interval, and of course, mean value theorem applies, so somewhere on that interval, we should also happen to have a place where the instantaneous rate of change is 5, or in other words, where the derivative is equal to 5. And that's exactly what we're going to try to find here. Mean value theorem applies. There should be at least one place in our interval, at least one point, where the slope of g, in other words, where g prime, is equal to our average rate of change that we found, that average rate of 5. So let's first find out what is g prime. And so for our function, it was x cubed minus 4x. And so for the derivative of that, derivative of x cubed is 3x squared. And derivative of 4x is just 4. We want to know where is g prime equal to the average rate of change that we just found, which was 5. So we want to know where is 3x squared minus 4 equal to 5. And I find that x squared is 3, or two possible values for x, positive root of 3 and negative root of 3. Now, we have to read the question carefully. We're looking just to find all the x and y points where this happens. I found the x coordinates. I guess next I need to find my y coordinates. So I'll do my two values separately. If x is positive root of 3, then the y value is g of root of 3. Notice we're going back into the original function. It's the original function that gives us y values. G prime gives us slopes. We're not interested in slopes. We know what the slope is. At root 3, the slope is 5. And we know that because we just found it. Here I want to find the y value when x is root 3, so I'm putting root 3 inside of my original function g of x. So I've got root 3 cubed minus 4 times root 3. Root 3 cubed is 3 root 3. And so we wind up with 4 root 3 minus 3 root 3, or negative root 3. And I'll do the same thing for the second point. I have, if x is negative root 3, then y would be g of negative root 3. Putting that into the original function, negative root 3 cubed minus 4 times negative root 3. Negative root 3 cubed would be negative 3 root 3. Negative 4 times negative root 3 is plus 4 root 3. And then when I add the two together, I get just root 3. So now we're getting ready to go. I can just finally state my answer that the 2 points happen to be root 3, negative root 3. That's the first point that we found over here. And the second point that we found over there was negative root 3, root 3. Both of these points are inside of our interval. Our interval was from negative 3 to positive 3. This is about 1.7-ish, and the other one is about negative 1.7. So both of those are definitely inside of our interval. So as predicted by the mean value theorem, we do indeed have at least 1 point. In fact, we have 2 points where the slope of g is the same as the average rate of change of g over the whole interval.